It seems to work. Okay. So yeah, we're very happy to have Daniele Condorelli from the University of Warwick Economics Department here today, kicking this term's seminar series, Algorithmic Learning in Games, off with his talk on deep learning in games, deep learning to play games. So please, Daniele, you have 1 hour plus 30-minute discussion, however you would like to distribute that. Take it away.
Thank you very much. It's a pleasure, and I'm honored to speak to this audience, and I hope I can get a lot of comment, and feel free to interrupt me any point. Can I ask you, do you see me in the video? Because otherwise
No.
Okay, good. Then I can walk and stuff. All right. So, okay, this is joint work with Massimiliano Furlan, who also participates at your meeting, and is a student, a PhD student at Warwick. Now, okay, let me explain what we do. This is a paper, we call it Deep Learning to Play Game. Let me explain what I do for an audience that understand both neural network and game theory, so hopefully for many of you, and then I'm going to explain everything in more details of what we do. So the broad idea is that we take two neural networks and train them independently or adversarially to play strategic game. So the input of this neural network is a bimatrix that represents a whole game. So both the payoff of player 1 and the payoff of player 2. And the output is a mixed strategy, let's say, for the raw player. And this network are trained to minimize their own expected regret through stochastic gradient descent. So essentially, a game is given to both networks. They output a strategy that they would like to implement, and then they look at the regret they obtain in that particular game given the opponent behavior. And if they did best respond, they don't do anything. If they didn't best respond, then they are going to change all weights or their parameters with the usual stochastic gradient descent algorithm in the direction that reduces the regret in that particular game. And then this process is repeated to a training set that is composed by many randomly generated games. Now, we see there is clear evidence of learning in the sense that these algorithms start at a regret which is 0.6 on average from playing just randomly, and end up to in 2x2 game to a number that is around 0.003. In fact, they learn to play pure Nash equilibrium almost perfectly, and to coordinate in one when there are multiple. And they also obtain good performance, but less good on when the only equilibrium is mixed. Okay. When it comes to 2x2, and this extends to 3x3 games and 4x4, etc. But of course, there is a curse of dimensionality here and computational issues when you get to larger games. And when we look at 2x2 game, there is a very strong prediction that the equilibrium that they coordinate to play is the risk dominant, their Sunny-Selten risk dominant equilibrium. And I mean, this phenomenon that they learn to play Nash equilibrium, we think is quite robust to a number of modifications that we have implemented, and including especially training on a subset of game, and then having a good performance on all games more generally. Okay, so this is the broad level summary. Now, why is this interesting? Or, I mean, there might be many reasons why this is interesting. One motivation that we use as our essential leading motivation for this paper is the following: is the well, we start from the observation that Nash equilibrium is the central concept in social sciences to a degree that is almost scaring, but but it's not a completely well-founded concept, or at least the epistemic foundation is not, that it has no proper epistemic foundation, and so it is not clear, in a sense, why should a player play Nash equilibrium to begin with, and this problem is even more important or compelling when there are multiple equilibrium. And so when you open a book of game theory, what you read is that, well, Nash equilibrium is a good concept because learning and evolutionary dynamics will tend to bring less than rational or non-equilibrium play agents to Nash equilibrium. And one example is that you have seen, I think, maybe in the first of your meetings, Galit, I think, discussed it, was fictitious play. So if players best respond to the empirical observation of the opponent's strategies, and there is a process, they keep updating their best response and this empirical estimate of opponent's strategy, play will converge, if it converges at all, which is not guaranteed, to a Nash equilibrium. Now, there is a problem also with this sort of motivation for Nash, and let me read here from some of the giants in game theory and writer of some of the big books in the area. So let me start with Krebs, that says, if we rely solely on the story of... Please.
Je vais arrêter ça. Elles sont.
Okay. So if there is a question, feel free to speak up. So if we rely solely on the story of directly relevant experience to justify attention to Nash equilibrium, and if by directly relevant we mean only experience with precisely the same game in precisely the same situation, then this story will take us very little distance outside the laboratory. It seems unlikely that a given situation will recur precisely in all its aspects. So someone has the microphone.
Yeah.
And so this story should be thought as of applying to a sequence of similar situations. And similar, Fudenberg and Levin, our presumption that players do extrapolate across game is an important reason to think that learning models have some relevance in the real world situation. So the point here is that all this learning in games, or most, or at least to our knowledge, in fact, if someone has different knowledge, please write it in the chat or speak up, work by assuming, except very few exceptions that I will cite later, work by assuming that players train on a single game. But of course, this story of learning within a single game is only a story that can be replicated in the laboratory. We never bathe in the same river twice, and so everything is every time different, and so we must be learning, extrapolating from related situation how to deal with games more generally. And so this bit of the and so in a sense what this model provides is a story, is a learning model that actually shows how you can learn to play Nash equilibrium without ever playing the same game, in a sense. Okay, and it is a classic learning model because there is some non-rational agent that whose behavior gets updated based on experience. Okay. And importantly, the model here and the result I will present are empirical, or in a sense, the result of a simulation. This is a hard problem to deal with without simulations. But of course, if someone has idea on how to sort of think about this problem analytically, that would be nice to know. And yeah, so one can formulate a conjecture that in fact this universal approximator through this process might converge to play Nash equilibrium, if not in all game, in almost all games. And yeah, okay. So is there other questions so far?
Daniele?
Yeah.
So I mean, I guess you're gonna show us this soon, but so you're minimizing some kind of regret score, I guess.
Yes.
Have you compared these results for a fixed game that you're getting against some simple bandit learners that are guaranteed to achieve no regret? Do you get more convergence than those? Like, it's known that these will not always converge to a Nash equilibrium. Might be correlated, might be no equilibrium at all.
We haven't done much computation. As I always say in this talk, once we will submit this paper, referees will go wild with what we should do. So we are waiting a little bit, but no, we haven't run a horse race of this against other algorithms at the moment.
I'm just wondering if some like standard theoretical predictions for no regret learners extend to this, or if there's something over and above that you're getting from the neural network approach.
No. Well, the point is that you need to deal with all games at once. So I think there are theoretical results when you're thinking about single games in isolation, or perhaps even a stochastic game playing repeatedly. But here, the object of interest is a function that goes from the space of all possible payoffs, let's say in a 2x2 or 3x3 game, into these mixed strategies, and so it's a much more complex object. So I don't think there are results. I would be curious, but I doubt. And also a key element that is different from classical learning model, if you think about Artem, Mascolel, and so on, is also this aspect that we allow observation of the opponent payoff during learning. Okay, so this is not something that a lot of these learning models have, and which gives rise to uncoupled dynamics, and so dynamics that do not allow for learning on Nash equilibrium, if I understand correctly.
I see. So the state is the whole game's or everybody's payoffs.
Yes.
I see. Okay, thank you.
So if you want to think about a situation of this sort, so to me this is the natural way to think about these game playing agents, because I mean, of course, when we start learning game theory, I mean, in a sense, you are given the whole matrix when you decide to play, and this is how experiments are run. So, and I mean, of course, it is, I think that how I would frame, for instance, the problem of strategic games that you encounter in traffic. For me, this is like a key example here. So in traffic, we do tend to play all sorts of very different strategic games all the time. But I mean, we figure out how we should react to a certain situation, and there are some equilibria that we play as a result of learning, which is a learning that comes having a view of the game being played completely. So, okay, so there are some papers that have worked some models of learning across games, and I mean, I hope I'm not making detracting them, but essentially either the space of game was treated as finite, for instance in Mengel, or there was an exogenous relation of similarity between games, so that in a way learning was by cases, like in Licalzi and Steiner and Stewart. So here, essentially, we have a learning model where the set of possible game is infinite, so the agent never gets to play the same game twice in our training set. And there is no exogenous relation of similarity across game, except of course the natural ordering given by the payoffs. Okay, so the idea of using a neural network for games as predecessors, and in particular there's this paper by Groy and Zizzi, in which they try to sort of give the best response directly and train in a supervised fashion the neural network to identify the Nash equilibrium. But they didn't get far, and so they didn't find the network Nash equilibrium. But of course, more modern work now show that Nash equilibrium is learnable. This Liu and others is a computer science paper by some people from DeepMind, I think. There are also some other researchers that have set up an environment close to ours, and in particular these two papers by Spiliopoulos. They also have a setting with a random generation of games and a regret function of sort. But being run in 2011, 2012, he was running them in his Pentium. Every simulation took him 1 month. And I mean, essentially, his main conclusion is that these players do not go to Nash equilibrium, and especially mixed Nash. And so his conclusion is quite different. And in fact, he attempts to characterize the behavior of the network. And you could go the other way around by thinking about using neural network to sort of fit human behavior. This is, for instance, this paper. And finally, there are other papers that, I mean, think about how the evolution of a rule to play Nash equilibrium. Sorry, not to play Nash, to play games. And experiment, which I won't go in details unless you ask, and experiments that do indeed show that there is learning across games. So there is something that is portable in the experience from playing one game and another. Very good. So let me start with the neural network. So I won't go into the details because I don't think we have a lot of time. But what I want to say that, and I think this audience should kind of know the broad idea. So essentially, a neural network for us is going to be a function. This is going to be a function parameterized by these parameters, which in this picture, they will be the W's. And essentially, the function takes as input the game and spits out a mixed strategy. So that's all it does. And essentially, the nodes here perform computation, and parameters are the weights in this linear computation that the nodes perform. And this is a composite function that is easy to differentiate for the parameter. Essentially, there are two properties, I think, that are notable about this particular functional form that is built up by this architecture. One is that it is a universal approximator of function, and two is that performing differentiation comes easy. And this is important during this optimization process. Okay, very good. So now we get to the core of our model, because this is how essentially these functions are updated. So again, let's start, and please here interrupt me, because this is the central slide of the paper, I would say, besides the results. So that two neural network will be represented here by this function f and I. N means the number of action, I is the player, there's only two players. And this function go from games into mixed strategy that are parameterized by this long vector of parameters. And they are initialized in a way that essentially generates a random behavior. And then they are fed with a sequence of random games that include the matrix of the player one and the matrix of the player two. And as I was explaining, the updating of the parameter broadly takes place as follows. You take the parameter from the previous period and you keep them the same if the agent is best responding to the opponent strategy. Okay. Now keep in mind that if the opponent is playing mixed, the agent will rarely or never best respond exactly, so there will be some updating process most of the time. Now, how this updating process takes place? Well, if I'm not playing a best response, then I'm going to check how each individual weights would affect my loss if I slightly moved it upward or downward. And this is done independently, weight by weight. That's why there is this gradient here.
I have a short question.
Yeah, please.
So maybe you said it, but do you observe the strategy your opponent, the other player, chose?
Yes. So this is where you build your counterfactual on. So here, okay, first of all, here in this slide, you get to observe the entire mixed strategy of the opponent. Now, in a robustness exercise, you get to observe only a realization of the action of the opponent. And there is still learning in that case. Now, since payoff really are generic here and randomly generated, if you were to observe your payoff, you were to essentially be able to make an inference on what the opponent did. And so we thought a minimum here, this experience of what the opponent does is essential to generate learning, to think about learning, to have a counterfactual of what I could have done to improve outcome in this game. So to return to our problem, then you...
short follow-up question?
Yeah, please.
So the output, the payoff you get is the in the mixed extension. It's not a realization of from the mixtures.
Correct. In this slide, yes. And in the result that I gave you, yes, I have some result at the end where we make the opponent realize his action. Now, what I wanted to say is that I don't think this is a huge deal, because essentially, even when the opponent plays a mixed strategy, you never exact best reply exacting with a mixed strategy. So the best reply will be always a pure strategy anyway. But I mean, this is important, and in fact, we did consider not giving access to the full mixed strategy, because the interpretation now this would be that this interaction have multiplied a lot of times, right? There's been enough sampling that you have figured out the mixed strategies. Does it make sense? Now, okay, yeah. So yeah, so the process is then classic gradient descent. So these parameters are only updated slightly at each given experience. And of course, remember that the network is learning in a single game by single game. So it is assigned meaning to these weights game by game with the small increments. And we square the loss in fact, this turns out to be quite important. Mostly what it does is now to make basically the changing weight proportional to regret. So you're going to do a bigger changing weight once you have a bigger regret. Good. And so basically we train this neural network across game. We keep feeding them games and continue this process for quite a large number of games, and then we get our trained network. And here is an illustration of stochastic gradient descent, perhaps not the best, but the idea is that, well, you are trying to match the red line with this blue line that is only parameterized by these two parameters. Then you draw one game, one number here, 0.2. You have your line W1 plus W2x. You see a loss that is the amount, is this green measure. And then you say, how can I change my parameter to do better? And then you change this parameter individually by taking derivative on whether they improve or increase or decrease your loss at that point. And you go on and on. Of course, you can see here that you're never going to get a good approximation with this function, but this is just to illustrate how this updating of parameters work, and this is that it is done observation by observation. In fact, in practice, we do it for a batch of games, I should add, but that's not crucial either. Okay, very good. So now, so of course, if both networks play the part of the Nash equilibria, then we are in a stationary point. Okay, so for every game they play in the Nash equilibrium, then we are in a stationary point. So of course, if one had to design for scratch this algorithm, one idea would be, okay, let me give you an algorithm that computes Nash equilibrium, and let's always play, I don't know, let's rank this equilibrium in some way, and let's play a certain equilibrium all the time. And this, of course, would lead to zero regret. So now what's important here is this learning aspect. And so how, I mean, it's not, what I want to argue is that it's not entirely obvious that these two networks would converge to Nash equilibrium, or would converge at all, in fact, because it is likely that if they converge to Nash equilibrium. Or someone is speaking? So I think the main difficulty is that, of course, the environment is non-stationary, so you wouldn't be that much surprised if the network were to learn playing against another player who's always insisting on a certain equilibrium, in fact, selection rule. Okay, and so the other network would learn to accommodate this selection rule. This is not surprising. What is most surprising is that this joint play is developing together a selection rule that is agreed between the two players. And I mean, of course, here the optimization landscape is not well behaved, as this is classic for neural network. And finally, also the function that we are trying to match isn't so well behaved either. I mean, it's not too bad, but isn't great because it's the map of a Nash equilibrium. So essentially, it's a fixed point defined in this space. And we know that there exists no continuous selection. And since this neural network are continuous and differentiable, essentially, we know that we cannot perfectly match any selection from the Nash correspondence. but we can still approximate. And maybe this comes back to the question on theory. Well, I mean, convergence, as many of you know, is hard even in games, even in situations where the agents are learning within a single game. And for neural network, some results are available, but mostly for what these are called generative adversarial network that are playing in an environment where they are playing essentially the same stochastic game, and they are playing a zero-sum game. Okay, good. So basically that was the theory. And now I'm going to move and presenting the results. Any question? I mean, I enjoy criticism, so if you want to tell me about model is not good or something, I'll appreciate. If not, maybe we can postpone this to the discussion. Maybe that's your rule. Let me report on the experiments which were run on Python with one of the classical packages for deep learning. So this network have 8 layers, dimension 512, but what's important is to say that the 2x2 game playing network has 2 million parameters, and the 3x3 game player has 33 million parameters. And we train the networks for 2x2 games on 1 billion games, and the 3x3 on 2 billions. And we get a lot of loss of performance from 2x2 to 3x3, but note that we didn't scale up the number of game match. Okay, what else? This is more or less what's the important things about the experiments. So let me report on the learning curve. So this is how the network learns in 2x2 and 3x3 games. So here we report after some steps the performance of the network in a batch of games and the average regret. And we start from average regret 0.5, 0.6, which is the regret from just random play. And you can see that this starts with a few period of, and note the scale is logarithmic here. It starts with a few period of no learning or chaotic learning, and then it enters a period of fast exponential learning. Now, we believe, I mean, we haven't checked the data for sure, but essentially here what they are learning is coordinating on games that have pure Nash. And then there is a phase of power law learning, which is the learning, we believe, of the mixed equilibrium, essentially. And of course, learning mixed equilibrium, sorry, we know it's easy, it's difficult, because, so the more you get close to the equilibrium, the less incentive you have to play that specific mixed one. So anything goes. Okay, so this is supposed to be some illustration of what the network does. It should go automatically, but since I'm doing this, I will do it by hand. It's a bit ironic. But so what we're doing here is that take just one game and parameterize it by X. So this is the game on the left. And then let's look at row player and column player. row player on top, column player below. And the red and the blue line are the network behavior. And the thick lines represent the Nash equilibrium mapping. And yeah, so as you can see, there is only one equilibrium when x is between -2 and 0.5. Then there are 3 equilibrium at 0.5, from 0.5 to 1. Okay, and then there is only one equilibrium again. And so we now want to check how the network behaves as we start training. And so basically step 1, step 15, nothing change. Once you get to step 39, nothing change. 125, nothing. Okay, so in 398 you see the network, they are doing something. Okay, and you can go on in this simulation, and you see now here they are starting to approximate much better the Nash equilibrium mapping, and you can see they decide to play the equilibrium on top. But in the middle there, they must be playing some mixed equilibrium as they move from one pure to the other. Where in fact in the middle way there's a mixed equilibrium there, from -1 to 0.52. Okay, and basically, let me go faster. Now they are, already, but yeah, they are quite playing equilibrium. Okay, so this was about the learning. How do we test the model? Well, we generate a random set. This is not so necessary because, of course, the network is already training on a random set of games. But anyway, we then look at how the prediction of our model compare to a bunch of, let's say, solution concept and other notions. Okay, and the key results are in this table. Essentially, what we see that the relevant measure here that we look at, there are two. One is the what would measure an epsilon equilibrium. So the maximum of the regret achieved by the two players at that profile of strategies. And so this is 0.003 when we look at all games. That means that essentially, on average, they would be playing 0.003 epsilon Nash. And you see that when the game is dominant solvable, so there is only one Nash equilibrium, then this goes to beyond the third decimal. So regret becomes very, very small. And in fact, yeah, this is essentially taking place in games that differ from each other, where a strategy of a player differs from the strategy of the other by very little. And yeah, so but you see that with when there is only mixed Nash, so we're at the 0 on the number of pure Nash, the regret increase substantially by a lot. Okay, and so this is a reflection that we are fitting pure equilibrium quite well, but we have a harder time with mix. But this is still evidence of learning. This is very far away from random play. And the other metric that we use is distance from the specific equilibrium action, but the numbers are analogous. Okay, so in 3x3 game, results gets worse, but to me they are still evidence of successful learning of Nash. Particularly, you see that in the mixed equilibrium, the error begins to be larger, but still very far away from random play. Okay, distribution of epsilon equilibria. Well, this is just some, essentially we look at the game by game in our test set and look at the maximum regret that is being achieved, and I mean, the 99 percentiles are represented by this dot, so essentially the max regret in 99% of 2x2 games is below 0.04. Okay, when there are all games, when there are no pure Nash, it doubles. Okay, and this measure worse in 3x3. Distance, same story. Of course, you may ask, okay, but how is the network performing in iterated dominance reasoning? And of course, it's playing Nash, so it must be performing well. And in fact, the mass placed on game where an action is dominated, 99% of game with a dominated action, the mass placed in the dominated action is below 0.02. And keep in mind that often when this happens, it is because one action is dominated by another by a very small amount. And you can think that the network here somehow needs to allocate its computational capabilities in between making this comparison between numbers and other required operations. And so, of course, at some point, there's no point to distinguish to the 5th decimal point. And so that's why we get this, that there's some, but essentially it performs very, very well on iterated dominance. Now, equilibrium selection, what we get, this is a bit of a tricky table, but essentially here in 2x2, it's simple. Risk dominant is playing 99% of the time, even in the presence of a payoff dominant equilibrium. And I mean, this is, I think, is an interesting result because it sort of vindicates their Sunny-Selten equilibrium selection theory. I mean, so it reinforces what we get from the learning literature on game by game. But mind you, here, what it is actually learning is an equilibrium selection criteria. It is not learning an equilibrium, so it's not learning how to play in a single game, but it is learning a rule to find and select equilibrium, essentially. And this brings us to the risk dominant one. Although later in life, not later in life, I think Sunny-Selten in their book, they ultimately say that, look, when a payoff dominant equilibrium exists, then we should go for that one. But they take the approach of a rational player as opposed to of a player that has learned behavior. Okay, with 3x3 games, the notion of risk dominance loses grip, and in fact, we find only 81% of our play conforms to it. Now, it might be that here is just a matter of convergence, or it may be not, but we don't know exactly. So we also tested how the network behaves in terms of some of the axioms that characterize behavior in game theoretical sense, and including equilibrium behavior. So one thing, so for instance, symmetry says that essentially if you flip the payoff of player 1 or player 2, they play the same. Okay, so these two networks, they learn to play the same thing. So the same mapping, even though, mind you, they are essentially experiencing very different games. So yes, they are playing the same game, but one is playing player 1, the other is playing player 2 in this chain of games. Equivariance is the property that, of course, in game theory, the order of in which you represent the action doesn't matter. Okay, so if you switch column and switch rows, then everything in the game theoretic analysis should remain the same up to relabeling. And in fact, our network do respect the property, although you could imagine that there was a scope for some sort of correlated equilibrium, because in a sense you might treat the order of action as some randomizing device that could be exploited by the agents. But we don't find evidence of that. And the last axiom that I want to mention is this independence of irrelevant action. So one question that you may ask is, okay, but is the 2x2 model behaving as the 3x3 model? And to test this, we basically built, you take 2x2 games, you enlarge them by adding dominated actions for the colon and row player, you turn it into a 3x3 games, and then you see whether the 3x3 players play as the 2x2. And we see that this is broadly the case. Then we performed some robustness on larger game, 4x4, 5x4 game, and a bunch of other alternatives. Now, the two important one here are the first two. So first we trained on a subset of games. So we cut the space of games, and then we trained the network on this subspace, and then evaluated on the whole set of games. And the other is what was mentioned before. We want to make sure that learning takes place even if I don't get to observe the entire mixed strategy of the opponent. So if I don't get to sample the opponent behavior multiple times from the same game, but I just see an action that is realized from this mixed strategy. Okay, so let's look at this, larger games, 4x4, let's keep it. I mean, of course, here there is a loss, but I mean, there is big evidence of learning. We don't report here the benchmark, but we should. I guess it's going to be above 0.6, but I don't know. And then we do a test of independence as before to make sure that this model, the larger you make them, they still agree with the smaller one. So they're actually still learning the same thing. And then here, basically what we do is that, I mean, this picture don't mean much. I like them because they break the flow of the presentation. They bring a bit of color. Massimiliano said they are meaningless. But essentially what we do here is that we are cutting the space of all possible games and then sampling only from, I think, 1/4 of the total space. And then we are going to look at how training in those subset of games allow for learning in general. And as you can imagine, it depends on how we cut these games. Because if we cut them in a way that that is fine, you get good learning, like in this case. But if we cut them in a way that, for instance, cuts out a lot of the mixed equilibria, then you don't get as good performance. So, I mean, again, the point is, of course, if I train you only on zero-sum game, which are dominant solvable, then you're not going to do well on extrapolating on other games. And so the question arises perhaps on what are the minimal set of games that provide good learning opportunities. Which games are really paradigmatic to allow learning of any game. And ex post regret loss is what you would expect it is, so you just get a realization of the opponent action. And as you see in 2x2 game, we get a decent loss, but there is clear evidence that there is learning. Of course, what gets much worse is mixed equilibrium. but still much better than random play. And in general, the equilibrium selection is still agreeing with the one when we sample the whole mixed strategies. Okay, bunch of other stuff that I mean, I don't want to tire you with it. So let me conclude with some of the how we play some specific games, and then I'll wrap up with some ramblings on what you can do, what this project may suggest. So this is how a prisoner dilemma is playing. As you would expect, it does well. The model prediction is the blue line, and then we list the Nash equilibria, and then how much regret is achieved, and we flag equilibria that are sunny-Selten, that are the payoff dominant equilibrium, and so on. Stagnant, well, again, you know what's going on because we know that it's going to play in the risk dominant equilibrium, and so they are going for the easy prey. Battle of sexes, you see, this is a symmetric game, so they are trying to go for the mixed equilibrium. Okay, and this is also the prediction over Sunny and Selten for games that are completely symmetric, essentially. But, well, again, here is not, yeah, so there's some ambiguity of what's going on. But remember that these are very, these are games that are very rare for the network because they contains a lot of all indifference and qualities that they never get to observe. In chicken game, well, they are playing an asymmetric one here. Someone is chickening out. Matching pennies, they do quite well, and perhaps above human ability to randomize, whatever that means. In the public good game, they do quite well. I mean, this is just a coordination game, essentially, with the possibility of deviating. And finally, rock, scissors, paper. As you see here, there is quite some loss, although they are not doing great. I'm not sure how human perform here if they attempt a randomization. Okay, and this is the Shapley game where they do even worse. There are other issues here, but let me conclude, and then we can discuss. If you have questions, we can go back to these points. So, well, okay, there is learning on Nash equilibrium, and they are going to the risk dominant one. So where do we go from here? Well, of course, there are a bunch of possible extension and that we may thinking about. There might be a theorem. We don't know. There might be a new selection criterion, perhaps, for 3x3 game and above. That is the resulting of this learning. One would want to extend this model to play extensive form games, and we are working on it a bit. It is much trickier because you need to feed this network with a representation of an extensive game. I mentioned that one possible avenue is to look at which games promote learning of strategic behavior. And finally, I think what this, now let me go back to this. Let me stop sharing. So what this might sort of perhaps suggest is that there is a theory of intuitive strategic behavior whereby when people are confronted with strategic situations, for instance, driving in traffic and so on and so forth, and they have an instinctive reaction, it might be that what they are doing is sort of figuring out, putting the outside world into a little game, and then make some sort of fixed point computation and extract from this computation an intuitive response. And I mean, I don't know. So I'd like to work with some experimentalists to try to see whether there is evidence of, because I think it is well recognized by psychologists that there is a lot of intuitive response in decision making, and that's natural because we learn how to behave, and then we respond. We don't stop thinking about, and in fact, not even chess players stops thinking about it a lot. A lot of times they just play. And of course, this intuition is generated to training, but one question is whether some sort of equilibrium computation goes on, and it might be that for very simple framework of very simple games that one could do, for instance, in traffic and so on, there is some sort of facility in our brain that attempts to solve this problem. And that's all I wanted to say. Thank you very much for listening.
Thank you, Daniele.
Thank you. Thank you to you
Thank
for
you,
this
Daniele.
great initiative.
Very interesting talk.
Thank you.
Let's open it up for discussion. So anybody who has questions, please.
Maybe I could start with one. Thanks, Daniel. Very interesting work and very nice presentation. So just maybe some very technical clarifications because the model was generally clear. So do these networks share parameters for different agents, or are they different networks so they can learn?
They are different networks. You could imagine this in autoplay too. But yeah, these are different networks. Autoplay would force symmetry in a sense.
Right.
But
and also the initialization. So you need an initial strategy for the players to start the training.
No. I mean, we were pretty lucky in the sense that this turns out to be a relatively easy problem for neural networks because these are like classic fit for when we were thinking, okay, let's plug in a transformer and whatnot, but there was no need of that. So these are quite simple network. They do the job.
They do the job well, right? From the result.
Yeah. So even I mean, now Massimiliano knows a lot more of the details of how these are implemented, but I think even simple random initialization of parameters, which is something completely discouraged in deep learning. There's a lot of strategy to get started, give good results. So I think this is just an easy problem for the networks.
Okay. But maybe you imagine as you go to larger games, there may be the transformer or
more
the extensive
complex
form
games for sure. For instance, when you think about the extensive form game, there's a clear time structure, sequence, and there probably you will get traction. I mean, again, and significant gain. I'm sure. I mean, there is a dimension. There is a geometric dimension also in games because you want to focus more attention on the payoff below you. because this is exactly where you're thinking about the deviation.
Mhm,
But
mhm.
so maybe transformer will do better on this problem. They do better everywhere. So, but that wasn't necessary.
Yeah, for the extensive form game, it makes a lot of sense with it. Great. And a final small technical question about the math. So in 3x3 games, the risk dominant is defined like in 2x2. So the equilibrium that performs best against the uniform distribution, let's say.
Yeah,
Okay.
in 3x3 is their Sunny-Selten procedure, and we are very grateful to Bernard von Stengel that gave us the code to do this computation in 3x3 games. Otherwise, but yes, it's like the Lemke algorithm starting from different priors initials.
Okay, great. Thanks a lot. Thanks again.
Thank you for your question.
So if I can come back to one of the questions about, whether the two neural network was the same or not. So I'm not sure to understand why in say a symmetric coordination game, I mean, they would go for the mixed equilibrium if these are not exactly, the same networks. So I would expect that at some point you get closer, to basin of attraction on one of the pure equilibria, then you go there. So
yeah,
what's
so
happening?
I think this is so. Now, first of all, also Arsani and Selten, when they say, look, what equilibrium should we select in this perfectly symmetric situation? They say, well, we need to select the mix. We cannot go for the pure to the right. We cannot go to the pure for the left. We need to go for the mix. So this is an extreme situation that you have described where everything is exactly the same. So where everything is exactly this. Now, why this situation you may end up in a mixed equilibrium? Because you always tend to go to a pure if you can. But then at some point when you are switching equilibrium, you need to start randomizing because this network has sort of continuous function. So you are playing a certain pure action, keep moving the payoff, playing a pure action, then at some point you need to switch. And when you switch, you randomize. And when you randomize, then you enter into playing mixed. Now, I don't know if this is very bad sort of explained, but I think it makes sense that you need to play mixed because essentially we are moving from one equilibrium to another by essentially that mix is in the perfectly symmetric game. The mix is exactly the point where you would jump when you pass from one to the other. Because if you raise the payoff a little bit, then one equilibrium becomes the risk dominant. If you raise it the other side, the other becomes risk dominant. And so when you go to the zero, there needs to be some smoothness. And this is what the mixed equilibrium does, I think.
Thank you. No,
Okay.
thank you. I was muted. Yeah, I need to think about it, but thank you for that explanation.
I like the idea of thinking about this like minimum selection of like what's the minimal set of games on which you could train. And I was wondering, so there is this recent paper by Davide Legacci and Mertikopoulos and Prodelsky about a decomposition. I can send you the, or maybe I can put the link on the chat or
okay.
Basically it's about a decomposition of finite games for some family of no regret learning dynamics into games where you can guarantee convergence and basically games where you can't, or you get chaotic behavior. And this includes, for example, the rock, paper, scissors game or the badly behaved like Shapley kind of game. These ones you wouldn't get convergence. You also don't get it for the deep learner. So like I keep thinking about like if you can relate the complex behavior you get here from this huge thing to something much simpler and where the essential differences are. But anyway, if there are not big differences, maybe it's enough to take that decomposition from that paper and only train on the, on the games that it can guarantee convergence on, or at least use that as a starting point for finding a minimal set that's sufficient. Or I don't know. I mean, at least for those where you can guarantee no convergence, you can just forget about them anyway. I don't know.
Yeah. I mean, these are very like the Shapley game was cooked to create non-convergence, and in fact, we do get some sort of rotation when we play the Shapley game. Okay, I don't know exactly what's the result we have there, but it seems like we run around the equilibrium.
Yeah, it's a very common kind of thing. Yeah. So I've just posted this on the chat in case it is helpful.
Thank you. And I mean, if any of you is working on this area, please feel free to reach out and thinking about this problem now, maybe not so much from a theoretical perspective, because this is getting a bit too difficult. But for instance, it would be nice to, I mean, I think what stops me is like imagining this function and thinking about how you would update this function in every point in a way that makes sense. The only thing that comes to my mind is, of course, you could grid the space of gates and then assign a weight to each cell and then learn within each cell and think about something like that. But this wouldn't work well, because once you cut a part of the game, then you don't know what to do there.
I guess another thing, I'm not so familiar with like the better known results in no regret learning, but I don't know if there is like a known selection thing about risk dominance there as well. I'm not sure if that's
so
an easy
mind you that
connection.
this I think a regret is a bit misleading the way. I mean, because there's various way to think about regret, and like often in computer science they mean, okay, suppose I change my behavior for all the game. Yeah, so this would be no regret if I change my Nash equilibrium mapping. How would I do well in all games now? And also there's this aspect that there's no attention to the payoff of the opponent. Now the state space would have to be, and this changes completely apparently the kind of result that you can get. Because of this Artin-Mascolel result, you don't need to go to correlated equilibrium anymore. So yeah, so seems I think I don't know, because this idea that you would rely on looking at the whole payoff to me seems natural, but I think the people who worked in learning, they had this idea that this object need to be very stupid and just receive its own stimulus through the payoff, and then of course then the payoff of the others make less sense to think about. But I think it makes sense when you think about counterfacts. But no. But when you look at how you should behave, you need to. The strategic situation includes what I mean. It needs to be part. When we are in traffic, we see some guy with the car that is destroyed, and we have a new car, and then we stop and we let him pass because we don't want to play the chicken game with him, and so I mean, so this is obviously I would say that this is part of the environment. It includes what we call the payoff for the other player.
And if I may add here, so and the transferable component that you also mentioned at the beginning is that the networks learn to best respond rather than, let's say, overfitting to a game and learning the Nash equilibrium. So they learn the concept of best responding sets in
Well,
some.
they must be learning even Nash. They must because when there are multiple equilibria, they are sort of figuring out what the other is playing, and to figuring out what the other is playing, they need to sort of think what they agreed on. I mean, now I'm a bit out of my depth here to make what's going on, but there is it's not best responding is not enough. They learn to best responding if they could. Because they never also see the same game, so it's not even clear what their best. They need to make a prediction of the opponent behavior when they see a game, and they best respond to that. So the two things need to go together, which in the end of the day is just you need to learn an action. I see a game, I need to play something, and this behavior gets ingrained in my brain. It's not that I'm making, but somehow what I want to, my hypothesis is that there is a representation of the strategic situation and some computation going on that I mean because that's the only way to do this mapping in an efficient way, because otherwise you cannot do it game by game. You need to have this approximate this mapping. Otherwise, how would you do?
Yeah, that's very interesting indeed. Yeah, that's very interesting. What they learn exactly. Yeah, thanks.
Yeah, I wonder also like how robust the selection is. You know, it makes a lot of sense, but how far can you push it, and can you push it for other selection criteria if you adjust the objective in some ways? Like, I wonder what the space of objectives is that gives you this versus payoff dominance or any other kind of.
We thought a bit about objectives, but it doesn't seem there's many. So imagine that. So suppose you weren't. I don't know. This objective is very close. Is payoff maximization within the single game. So the point is, when you accept that you have seen the outcome of the play is going to inform your behavior, then in which way you can inform your behavior? Well, you need to be modifying yourself as a result of your observation, but your observation need to either include your own payoff or the behavior of the other. And when you modify yourself, I mean, you need to go in some direction. And what's the direction here is the direction of, okay, I could have done this and obtained this, or I could have done that. So I haven't figured out an alternative to this. Another thing I want to say about payoff of the opponent. Suppose you didn't see the payoff of the opponent. Well, then you would just think that the opponent is randomly playing. So you would just go for the action that gives you, because it is randomly playing, because it's playing random games. So we are playing random games. I don't know which games you're facing. From my perspective, you're playing randomly, whatever thing you're doing. And so I would just go for the set of action that gives me the higher payoff on average. But then if games are randomly drawn, I'm also playing randomly. And so at the end of the day, we would be both playing randomly. This would be some sort of an equilibrium of this situation. So there would be no learning in this setting, because there's no way I can predict the opponent behavior if I don't see his payoffs.
Yeah, I guess you can find an in-between place where you give some signal about, you can flag whenever you keep your own payoffs fixed, there's 10 flags you have. But those are different ideas about the incentives of the opponent, and then I don't know. But yeah, that would push it a bit far. I mean, that's not really the point, I guess.
Yeah, no, that would.
Yeah.
So one thing we want to do, for instance, is to have. I mean, you could try correlated equilibrium here easily. Like, I mean, suppose they observe a randomizing device, then they would play correlated equilibrium, and yeah. So but I think the most promising at this point is extensive form, because also Nash is not is much less on secure ground than it is. I mean, it would have been weird. Anything else than Nash would have been borderline absurd in my perspective. I mean, there cannot be any. I mean, if these people are not playing Nash, I mean, they leave something on the table. And so why are they leaving something on the table? And then this would be a pathological learning, which might as well happen, but then I wouldn't be so happy about my machines, so to speak. And yeah, and there in extensive form games, you don't, I mean, what learning means is much more controversial, because you might fail to explore and never play the right way. So you go to self-confirming equilibria, for instance. And so it might be interesting if we get to self-confirming equilibria, so Pierpaolo gets all excited about it. And yeah.
Okay.
Okay, I will end the recording here.
Yeah. Thank you. It was very interesting.